So we've been working our way through a series of 2D particle equilibrium problems. And we've used cables and we've used struts. We've had members in tension. We've had members in compression. We've done multi-node problems where we started a particular node and then worked our way through it. All of those are basic skills that you need to do to be able to analyze trusses. And so in this class, we're currently in chapter 3. But once you actually get to chapter 6, which is trusses and frames and machines, then trusses, there's two methods to analyze trusses. One is joints. And joints are particle equilibrium. It's the exact same thing that we already did here. We started a joint, find equilibrium at that joint, and work our way to the next joint. It's the same thing that we did on that backhoe problem. Treat that as a joint. We can isolate that joint and apply equilibrium there. This is a truss problem. And it's a tower truss. It's anchored on the ground. I've got a couple forces acting on up here at these joint A and joint B. I need this angle theta. The tangent of theta is 1.25 over 3, and so theta is 22.6 degrees. And these truss members, I need to show you this. This looks like A, B, C, D, E looks like a single member, but it's not. Each of these members is a separate member. So AB is a separate link with a pin at A and a pin at B. And then BC is a separate link. AI is a separate link with a pin at I. BI is a separate link. IC is a separate link. IH is a separate link. CH is a separate link. So all of these are pinned together. And we've got the 4 here, and we've got the 6 here. And so if these are all pinned with pins, if they're all free to rotate, and if they're all weightless or massless, then these are all two-force members. And basically, they have a force that acts along their line of action. So if I draw the free body diagram of pin A, and I know that I have 4 kilonewton load that acts that way, 4 kilonewton. I know that this FAB acts along that line, FAB. And I have FAI that acts along this line. I don't know whether they push or pull or not, but I know that they act along those lines. Once you get that figured out, then you can just basically set an X and a Y coordinate system. If you mentally sum forces in the X direction at A, it's clear that FAI has to push on A so that his X component is exactly equal to 4 and balances A in the X direction. Then if you mentally sum forces in the Y direction at A, the only one of these forces with a Y component is FAI acting upward, and so FAB has to act downward. And this is 22.6 degrees. So this is the thought process in getting the free body diagram and assuming the correct directions on these forces. Once you get them, then you can sum forces in the X direction. 4 minus FAI sine 22.6. FAI, excuse me. FAI is equal to 10.4 kilonewtons compression. Sum forces vertically. You've got FAI cosine 22.6 minus FAB is equal to 0. And so FAB is 9.6 kilonewton. He's pulling, so he's in tension. This guy's pushing, so he's in compression. So now we started at A, And we've got these two guys. Now, you can actually step down to B. And so if you draw the free body diagram of joint B, we've got, and B will look like this, basically. You get the pin B, and you get the vertical components, and then you have those horizontal components at B. This is 6. And it's pretty clear that FBI has to act the opposite direction for B to be in equilibrium in the x direction. And so he's equal to 6 kilonewtons. And since he's pushing, he's in compression. AB, we just found to be in tension and equal to 9.6. And so if he's pulling on A, he has to be pulling on B, so he acts up on B. And so this is FAB is equal to 9.6 kilonewtons. And of course, he's in tension, he's pulling up. And so for B to be in equilibrium, then you know that FBC has to be 9.6 kilonewtons, also in tension, to keep him in equilibrium. And so we started at A, then we did B, then we can step to I because we now know AI and BI. We're now down to 2 unknowns here, so we can do I. And we can just keep walking our way down the truss. And at each of these joints, we're going to do what's called joint equilibrium, or the method of joints. But it's really the particle equilibrium, which is the same thing that we've been doing here in Chapter 3. And so I wanted to show you that what you know now, it will be directly applicable to trusses in Chapter 6.